In this video, we're going to begin discussing molecular orbital theory. So similar to valence bond theory, molecular orbital theory is a method for determining the structure of a molecule as well as how the electrons are distributed around that molecule. However, there are some important differences between the two theories. Let's just briefly review valence bond theory. According to valence bond theory, the atomic orbitals of two atoms bond together by overlapping and forming a covalent bond. Each of the bonding atoms, however, maintains its own atomic orbitals, and of course we know an atomic orbital, according to quantum mechanical theory, is a physical region around an atom's nucleus where there's a 95% probability of finding an electron. So if we have, according to valence bond theory, two hydrogen atoms would form a covalent bond by overlapping their atomic orbitals. Each atom still maintains its own atomic orbitals. Same thing with fluorine. If two fluorine atoms bonded together, their atomic orbitals would overlap in order to form the fluorine molecule, and the covalent bond would be formed by the region of overlap. Now, sometimes in valence bond theory, of course, our atomic orbitals are sometimes hybrid orbitals, undergo hybridization, but each atom maintains its own atomic orbitals, and they overlap these atomic orbitals to form a covalent bond. Now, this is very different than molecular orbital theory. So how is it different from valence bond theory? Well, there's three important points that we want to discuss here related to molecular orbital theory. First, when we form a covalent bond, the atomic orbitals of the atoms that are forming the bond, the atomic orbitals combine to form molecular orbitals. So the atomic orbitals do not just overlap, they form brand new orbitals called molecular orbitals. Now, these molecular orbitals, when the atomic orbitals combine, they can combine in phase or out of phase, because remember, orbitals or electrons have properties of waves, and they can combine in phase or out of phase. If they combine in phase, they form what's called a bonding molecular orbital. If they combine out of phase, they combine to form an antibonding molecular orbital. Now, we'll discuss what these mean in more detail in just a minute, but make some notes of these important points. Another point, the number of orbitals that combine must be conserved. So if we react two atomic orbitals, we form two molecular orbitals. If we combine four atomic orbitals, we must form four molecular orbitals. And finally, when we have our molecular orbitals, we place electrons in these orbitals according to Aufbau principle and Hund's rule, just as we would with any other quantum mechanical model. So let's start by discussing what is a molecular orbital. So how is a molecular orbital different than an atomic orbital? Well, when in molecules, atomic orbitals combine, so atomic orbitals react to form molecular orbitals. Instead of an orbital just surrounding an atom, molecular orbitals surround the entire molecule. A molecular orbital, therefore, is a physical region of space not around the atom, but around the entire molecule, where there's a 95% probability of finding an electron. In a molecular orbital, electrons are not assigned to individual bonds between atoms. So instead of an s, a p orbital, these orbitals disappear, and the electrons are treated as moving under the influence of the nuclei for the whole molecule. So the electrons are not just localized to individual atoms. Instead, the electrons are free to move around the entire molecule. Put another way, the electrons do not belong to the bonding atoms. Instead, they belong to the whole molecule. So this is a very different thought than we saw with valence bond theory, which maintained atomic orbitals. Another way to say this is that since electrons are free to move around the entire molecule, the electrons are said to be delocalized. So let me just try to show you this visually. Here we have two hydrogen atoms, and we have their atomic orbitals. These atomic orbitals combine to form two molecular orbitals. This one would be bonding and this is antibonding. Again, we'll discuss those more in just a minute. But here, instead of just the two orbitals overlapping, the atomic orbitals form brand new molecular orbitals, and the electrons are free to move not just around the atoms, but they're free to move anywhere around the molecule, either in the bonding or in one of our antibonding orbitals. So this is one bonding molecular orbital. This is actually one antibonding molecular orbital. We'll discuss those next. So atomic orbitals can combine in phase or out of phase, forming bonding or anti-bonding molecular orbitals. So what are these? According to the quantum mechanical model of the atom, electrons, of course, have properties of waves. Therefore, electrons in the atoms that are bonding together can combine either in phase constructively or out of phase destructively. So if they meet in phase, we have constructive interference, and out of phase, we have destructive interference. So just a couple of quick notes about those. If they meet for constructive interference, the two waves must meet in phase. Where the two waves meet out of phase, we get destructive interference. If they meet constructively, the waves reinforce each other. So we end up with a larger wave where the two waves reinforce each other. Where they meet destructively, the waves cancel out and we end up with what we call a node. Constructive interference, the waves give rise to a wave of greater amplitude. If they meet destructively, the meeting gives rise to a wave of a smaller amplitude or zero amplitude. So here you can see it visually. Here we have two waves, this wave, and they are in phase. If we combine these waves, we end up with a wave of greater amplitude. If you look here, the amplitude here is greater than the amplitude here. Here we have waves that are meeting out of phase, and we end up with the waves canceling each other out to form a node. Now remember, since we're talking about not just waves, but electron waves, the amplitude here is related to the probability of finding an electron in that region. So where we have a greater amplitude, there's a greater probability of finding an electron. And where there's a zero amplitude, we have a node or a region where there's a zero probability of finding an electron. So let's look at these bonding and anti-bonding molecular orbitals in a little more detail. So if the atomic orbitals combine in phase, they interfere constructively, and a bonding molecular orbital is formed. A bonding molecular orbital will have lower energy than the atomic orbitals from which they were formed. The lower energy is attributed to the increase in shielding of the nuclear repulsion because of the increase in electron density between the nuclei. Now that's a mouthful. Let me try to explain that. Here we have, let's say, hydrogen. We have two 1s orbitals, and those are going to combine. So those combine, and let's say they combine in phase. If they combine in phase, we end up with a bonding molecular orbital. So we end up with a lower energy. The bonding molecular orbital, you can see, is lower energy than the two atomic orbitals that formed it. So this is a more stable, lower energy orbital. Furthermore, where the electrons meet, when they meet in phase, we end up with a region right in between the two nuclei where there's an increased probability of finding the electrons. So the electrons are more likely to be found in between the two bonding nuclei. Since the electrons are between the two nuclei instead of on either side, the electrons shield the two nuclei from each other. So if the electrons were not in here, the nuclei would repel each other, and we would have a very unstable molecule. But because we have an electron density in between the two nuclei in this bonding molecular orbital, the nuclei are attracted to those electrons and do not repel each other. And so we end up with a more stable molecule when we have electrons in bonding molecular orbitals. Well, let's look at antibonding molecular orbitals. If the atomic orbitals meet out of phase, we end up with antibonding molecular orbitals, sometimes abbreviated as a sigma star orbital. Antibonding moleculars have higher energy, and you can see that here. They're higher energy than the atomic orbitals from which they're formed. And the higher energy is because when they meet out of phase, when the orbitals meet out of phase, they cancel each other out where they meet, which would be between the two nuclei. So we end up with a node here. So when we have electrons in antibonding molecular orbitals, there is no electron density between the two nuclei. So the electrons are going to be found predominantly over on either side of the nuclei, and there's going to be a lot of nuclear repulsion. So when these two when these two atomic orbitals meet, we form both bonding, one bonding and one antibonding. The electrons are going to preferentially go into the bonding first, but when they're full, then the electrons will go into the antibonding. Electrons in antibonding orbitals destabilize the molecule because the nuclei begin to repel each other because the electron density is on either side of the nuclei. So let's just try to sum that up here, since that's a rather complicated subject. When we have a bonding molecular orbital, the two atomic orbitals meet together and react. They overlap and they meet in phase. So where they meet in phase, they form a molecular orbital, sometimes called a sigma bonding molecular orbital, and there's an increase in electron density between the two nuclei. So in a bonding molecular orbital, the electrons are more likely to be found right in here between the two nuclei. That creates for a very stable orbital because the electrons shield the two nuclei. When the orbitals meet out of phase, where they meet in between the two nuclei, they cancel each other out, forming a node. And so you have the electron density when you have electrons in bonding molecular orbitals. The electron density is on either side of the nuclei, and so there's a lot of nuclear repulsion. So electrons in bonding molecular orbitals stabilize a molecule. In antibonding molecular orbitals, they destabilize the molecule. So how do we know where the electrons are going to be? Are they going to be in the bonding or antibonding molecular orbitals? Well, we want to look at that, and one way that we can look at where the electrons are a little more easily is to draw what's called an energy level diagram. This energy level diagram is just a simpler way of representing what we see over here. So over here on this side, we have our atomic orbital for one atom, and on this side we have the atomic orbital for the other atom. In the middle, we show our molecular orbitals. So the two atomic orbitals, in this case 1s orbitals, the two atomic orbitals will form a bonding 1s, so a sigma 1s bonding molecular orbital, which is lower energy, and they'll also form an antibonding orbital, a sigma star 1s molecular orbital. And the electrons will preferentially, as we'll see, go in the bonding first. When it's full, they'll go up into the antibonding molecular orbital. Electrons down here in bonding molecular orbitals stabilize a molecule. In antibonding, they tend to destabilize the molecule. Now, although we're showing here, just introducing this concept, showing s orbitals, p orbitals can also combine to form molecular orbitals. We can form p orbitals can combine to form bonding and antibonding molecular orbitals, and we'll discuss that in another video. So how do we know where the electrons are going to be? Well, as we mentioned, they're going to fill these molecular orbitals following the Aufbau principle and Hund's rule. We know the Aufbau principle tells us the electrons occupy the lowest energy orbital possible. Hund's rule tells us the electrons in the same sublevel or same orbital occupy they'll occupy the empty orbitals rather than pair up. So electrons in the same sublevel will put one electron in each sublevel. Then we'll go back and start doubling up before we move on to the next one. So let's take a look at how this applies to molecular orbitals. So we said that with hydrogen, our hydrogen atomic orbitals will combine to give us a bonding and an antibonding molecular orbital. The electrons are going to go into our bonding orbital first. So this hydrogen atom has one electron. This hydrogen has one electron. And so those electrons are going to go into the bonding molecular orbital first. Now, if we had additional electrons, then we begin to place them in the antibonding. But each orbital, just as previously, each orbital can only hold 2 electrons. So let's show this using our energy diagram. Here we have a hydrogen atom and its 1s electron. Here we have our other hydrogen atom. When those atomic orbitals combine, we form our bonding and our antibonding molecular orbitals. We've got 2 electrons to place. Those electrons will go in the bonding first with opposite spins. If we had more electrons, then those electrons would go into the antibonding until it was full. So hydrogen, its molecular electron configuration would look something like this. We have a sigma 1s bonding molecular orbital, and we have 2 electrons in there. So that's kind of like writing, we used to write 1s2 when we were writing electron configurations for atoms. Now we're writing electron configurations for molecules. So see if you can draw the energy level diagram for helium molecule using the energy diagram that we just, a similar one that we just discussed. So pause the video and give it a try. Okay. So first thing we want to do is draw our helium atoms on the side, and this is their electron configuration. Each helium atom contains 2 electrons. They will combine, these 1s electrons will combine to give me a bonding 1s, a sigma 1s bonding, and a sigma star 1s. So our electrons are going to go in the lowest possible energy level first, the bonding. Then we still have 2 more electrons. So we have 2 electrons, 4 electrons that we have to place. So the next 2 electrons will go up in our antibonding. So the helium molecule, as we'll see later, is not very stable because it has 2 electrons in the bonding molecular orbitals, but it does have a lot of electrons in antibonding molecular orbitals, which tend to destabilize the molecule. So although this is molecular orbital theory is somewhat complicated, be sure you understand the terms and definitions that we discussed, molecular orbitals, bonding, antibonding molecular orbitals, and also be able to write these energy level diagrams for a given molecule.